Today we're doing 3.2, solutions of linear homogeneous equations and the Wronskian. So today is all about finding, determining if you could even have solutions, essentially. And the way we determine that is whether or not the Wronskian is equal to 0. And we're also going to talk about intervals where solutions could exist or not. So in a second order linear differential equation, we know that our solution to this at some value of t is going to be equal to c1 y1 at that value of t plus c2 y2 at that value of t, and that the derivative at that same value will have a solution which, like we were doing in the last section, this will create a system of two equations. So the way to check if there is a solution or to even solve a system of equations is using Cramer's rule, or solve for a matrix, I guess we could say. So Cramer's rule, we don't need when they're like simple two variable, two equation systems. But when you get to having third order and fourth order differential equations, doing a system of equations for those is going to get really complicated. So you want to have other solving techniques. So we're going to teach you how to solve this when it's a simple one that you can check the solutions for, so that when it gets more complicated, it's a little bit easier for you. So the Cramer's rule is a method to solve systems. So say you have a system of equations that you're putting into a matrix. So matrix form, the typical, if you have a capital letter, it's a matrix. And then these are vectors, they're column vectors. So looking at our equation we had before, we're going to have y1 at t naught, y2 at t naught, and we're going to have y prime 1 at t naught and y2 prime at t naught. And then the coefficients are what we're trying to solve for. So we're trying to solve for C1 and C2. If we did matrix multiplication, we'd be multiplying the row times the column. And so when we multiply the row times the column, we get back to originally what we started with. And then it's equal to y1 at t1, or y at t1 and y prime at t1. We were saying t1, I meant t naught. So this is our system of equations. How Cramer's rule solves this is Cramer's rule gets these, can solve for any c, so any of these, C1, C2, if you had C3 or C4, by finding the determinant of replacing the whatever C value column in our matrix with what it was equal to. Essentially, Cramer's rule solves for that C value by taking the determinant of taking the A matrix and replacing it with the ith column and dividing it by the determinant of A. So taking the ith column of A and replacing it with the vector B. So taking the ith column, so for example, C1, we are taking the first column of A and replacing it with B. We're going to have Y. Sorry, this should not, I think it looks like it has a prime. It should not have a prime. We're going to have Y at T naught and Y prime at T naught. And then everything else stays the same. And then I have the vertical bars because I'm doing the determinant and dividing by the determinant of the original A matrix. And a reminder to solve a 2x2 determinant. If we have A, B, C, D, and we solve this, we're going to multiply diagonally and subtract the multiplication going the opposite way up. And that would be the determinant. So then think about in the Wronskian, Wronskian's basically taking, well, think about in Kramer's rule, what would make this not be zero, or what would make this not be solvable, as if that was equal to zero. So Wronskian's essentially putting a name to the process we're doing. So the Wronskian says, if we have some function f and g at t, then we can put f in row 1, column 1, g in row 1, column 2, and then their derivatives respectively go down, which is what we have going on here. We have our first solution, our second solution, and then their derivatives respectively underneath them. And this Wronskian is going to end up equaling f times g prime minus g times f prime. Sort of looking like the numerator of the quotient rule. That's it backwards, I guess. So two solutions form a general solution. So we get our general solution, and then we know that it will satisfy our initial conditions. And we should have that the Wronskian does not equal 0. The Wronskian is the denominator. This is in the denominator. When we're doing Kramer's rule. So as long as we don't divide by 0, then we should be able to have a solution. So let's first try to find the solution for example 1. So this is F, essentially, and then this is G. We're doing the Wronskian of F, G. We'd have e to the 2t, and e to the negative 3t over 2. So put those functions into your matrix with determinant brackets, because you're going to find the determinant. Okay, and think, what is the derivative of e to the 2t? 2e to the 2t. Derivative of e to the negative 3/2 t, negative 3/2 e to the negative 3/2 t. Okay, find the determinant. So you'd have negative 3/2 e to the 2t times e to the negative 3/2 t minus 2 e to the 2t e to the negative 3/2 t. We're multiplying variables that have the same, well, e is a number, but we're multiplying things that have the same base. So we add the exponents. It says 4t over 2 minus 3t over 2 is just t over 2 for both of them, both terms. So we get negative 7 over 2 e to the t over 2. Does this equal 0? Obviously not. So because this does not equal 0, then there are solutions that exist. Let's actually try to solve one of these. Okay, so the thing with these that I think is kind of gets a little complicated is that we have to find, we haven't done this yet, but we have a fundamental set of solutions. So if you look at the example, it doesn't tell you the y value or the derivative. So we're kind of leaning on this fundamental set of solutions definition. So the fundamental set of solutions says that y1 is a solution when we put in the t value, t naught value, so in this case we're putting in 0 into our solution, and we're saying that the y values are equal to 1. And then we're taking the derivative of that first solution and saying that when I plug in whatever our t naught value is, that it equals 0. So that's our first set of solutions. Then we have to do essentially the same thing, y2 solutions, but now flip-flop it and say that the original y value when we plug in t naught is equal to 0, and then when we plug in t naught to the derivative is equal to 1. Why this works is because then you have like 1 for both the initial y and for its derivative, so you could factor that up depending on what, it's kind of like the unit circle and how the unit circle works. As long as it has 1 unit, then you can factor it higher, multiply it higher if you need to. Okay, so first thing we want to do is solve the second order linear differential equation. So So we're going to do our characteristic equation. And factor. We get y1 is equal to e to the negative 3t, and y2 is equal to e to the negative t. Now what we're going to do is check to see that there are solutions. AKA, we're seeing if the Wronskian does not equal 0 with these two solutions. So we get e to the negative 3t, e to the negative t. Take the derivatives. Find the determinant. Negative 4t minus negative 3 gives me 2e to the negative 4t. And that does not equal 0, so therefore a general solution exists. If you got that equals 0, then there's no solution and you just stop. Alright, then we want to set up our general solution. Remember, in the general solution, you're saying C1, Y1 plus C2, Y2. So our general solution here is going to be C1, Y1 was e to the negative 3t, plus C2, Y2. And its derivative, we also want to find, so that we can start doing the fundamental set of solutions. Okay, so now we want to find, we're going to do assumption number 1 and assumption number 2. So here's assumption number 1. Step 4 is basically going to do this, and step 5 is going to be using this assumption. The only time we're doing this is because we said at this t naught value, at t naught equals 1, we didn't know what the y's were doing. So we're just trying to be able to come up with some fundamental solution that should work no matter what. And while I'm thinking about it, the fundamental set of solution gives us y star 1 and y2 star. And these form our fundamental set. So we would say y at t is equal to C1 y1 star plus C2 y2 star, and this is going to solve this differential equation no matter what the y value is equal to. So we're going to try to first get what y1 star is equal to. So we're assuming y at 0 is equal to 1. And y prime at 0 is equal to 0, and we're going to find y1 star for the fundamental set of solutions. Okay, so with that assumption, we're saying 1 is equal to C1 e to the 0 plus C2 e to the 0. So 1 is equal to C1 plus C2. And that 0 is for the derivative. 0 is equal to negative 3 C1 minus C2. And solve the differential equation. All right, C1 is equal to negative 1/2. Plug that back in. C2 is equal to 3/2. So that makes y1 star equal to negative 1/2 e to the negative 3t plus 3 over 2 e to the negative t. Okay, do the same thing but for our second assumption. Where y at 0 is equal to 0 and y prime at 0 is equal to 1. So we're saying still from this general solution over here. So we have 0 equals C1 plus C2 and 1 equals the negative 3 C1 minus C2. Okay, so we get C1 is equal to negative 1/2 and C2 is equal to 1/2. Wow, the little modem on my docking station for my computer was just so loud. Now that it stopped whirring, my ears are like, oh, thank God, so loud. 3, 2. I'm plugging this back into my general solution now that I have these two C's. 1/2 e to the negative t. Okay, then form your y1 star and y2 star form the fundamental set of solutions. Remember, we are saying that this is C1 y1 star plus C2 y2 star. So C1 times y1 star plus C2 y2 star. You don't combine like terms or anything, you just leave it like this. So again, this is just only needed if we don't know the y value for the initial condition and its derivative, its by condition. Okay, now we're going to deal with existence and uniqueness. So if we have a second order linear differential equation, one thing I'm going to point out to you is that the coefficient in front of our second derivative is 1 in this theorem, and that you need to make sure that that happens. Also, if you compare what's happening here to what we're used to dealing with, usually we have P of t, capital P of t, plus Q of t prime plus R of t y is equal to G of t. But now they've divided everything by P. So P of t, so really Q of t over P of t is equal to lowercase p. And R of t over P of t is equal to lowercase q of t. A little unnecessary, but like, well, it is necessary, but you do need to figure out, like, when I divide everything by that very first, I guess we could call it a leading coefficient in front of the second derivative, I think it's unnecessary that they use the same letters, just capital and lowercase. I find that to be a little bit annoying, but whatever. When we divide and we are looking at our P and Q, lowercase p, lowercase q, if they're continuous functions on an open interval, then there has to exist at least one solution, exactly one, solution on that interval. So that's the uniqueness theorem. So looking at example 3, here's our second order differential equation. And we are seeing in whatever, we're trying to find the smallest interval that contains our t dot value. So first thing, that's continuous. So first thing, we're going to divide everything by t minus 1. Okay, so we're checking both variables. Does t contain any discontinuities? Hopefully the answer is yes. At t equals 1. So the possible intervals, and is y discontinuous anywhere? No. All the y's are just derivatives and polynomials. This is linear, so it won't have that issue. So we have possible intervals for t. Intervals. You have negative infinity to 1 and 1 to infinity. And where is our initial condition? T naught equals negative 2. So we would be then picking, this is the largest possible interval where a unique solution would reside. All right, let's try to do 4 before I do it. This is a little bit trickier. So it's discontinuous at x equals 2, and tangent is not a continuous trig function. Tangent, where is tangent undefined? On the unit circle, where is the y over the x going to be 1 over 0 or negative 1 over 0? Pi over 2, we have the ordered pair 0, 1. So that's all the pi's over 2. So we would say all the pi's over 2 would be k pi over 2, where k is odd. Say it like that, or k, make sure this makes it be odd. This is actually like the definition of odd numbers, and I had to take a proofs and logic and mathematics course, and we had to prove even and odd. It's like such a common proof, and I had never seen this before, so that was kind of annoying. So maybe if you're going to take any kind of like proofs based class, it might be nice to know that this is what an odd number is defined as, because think about it, all even numbers are 2 times whatever number would make this be even. It's like that's the definition of even, is that it's divisible by 2. So then what's the difference? Then we just add 1 to make it odd. You could subtract 1, it's just usually we add 1 so that way if we're starting at like 0, we're not going into negatives. It doesn't really matter though. Or you could define this as pi over 2k, or pi over 2, and then how often it happens for the period of tangent. And again, k now in this case would be just an integer. And if you're not sure what symbol this is the integer symbol. Okay, so let's start listing out some possible intervals. And we're looking at our initial condition is 3. So we could say like negative 3 pi over 2 to negative pi over 2, but that's nowhere close. So let's just do negative pi over 2 x pi over 2. And then pi over 2 is 3.14 over 2, which is like 1 point something. So 2 is bigger than pi over 2. And 3 pi over 2 is like 9 point something divided by 2 is like 4 point whatever. If you wanted to do more, you can. Keeps going both ways of intervals. But what possible interval is 3 in? 3 is in this interval. Okay, that's all.